Okay, welcome back. We are going to go into chapter 3 now, and we're going to continue our look at linear programming. As I've said, linear programming is really the most powerful form of optimization modeling, and so we're going to spend quite a little time on it. And today we're going to look at network models. So let's go ahead and get started. So the other three programming models that we've looked at in terms of linear programming are the allocation, covering, and blending models. So the network model is the fourth kind of main model for linear programming, and it describes the flow of a connected system. Now, as you know, in supply chain management, we have the flow of materials and money, information, people. Okay, any type of connected system has things that flow, and typically any kind of a flow has a cost associated to it. And so often a network model will be concerned with minimizing the cost of the flow of a system. One of the things that we will introduce in this chapter is the concept of flow diagrams that we can build as a precursor to actually building the spreadsheet model. And it's not always necessary, just like doing the algebra is not always necessary when you're building a linear model, but often it helps. In fact, I find that flow diagrams help more often than doing the algebra. Okay, so one of the classic network models is the transportation model. And as I said, in supply chain management, the movement of goods represent cost. Okay, and so we try to figure out the movement of goods along certain routes in order to achieve our objective and yet minimize the cost. Okay, these problems are kind of classic problems in linear optimization, and so the models that we're going to talk about lend themselves well to it. So here we have Goodwin Manufacturing, which is an example, really it's an example of a classic transportation model. Okay, this is how it is laid out in the data. It's usually presented in this way. We have a number of plants that ship goods to a number of warehouses. Okay, in the rows we have our sources and our capacities. Okay, in the columns we have destinations with demands. So for example, Minneapolis can ship no more than 10,000 units. Atlanta requires 8,000 units. All right, and so in the middle we have our matrix of costs. These are per unit costs. So whatever Goodwin makes, if they make it in Minneapolis and ship it to Atlanta, it costs 60 cents. All right. And so the whole idea is to fulfill demand while remaining within capacity at the absolute minimum cost. And that's what the transportation model allows us to do. But before we do that, we're going to create a flow diagram. Okay? And so this is the way it works. In a flow diagram, you start by drawing a bunch of circles. All right? And each circle is a node and represents a location. Okay? So MPT on the left represent our sources, and ABCD on the right represent the first letter of our destinations. Okay? Then we start drawing lines, or in this case, we call them arcs, even though they don't really arc. Each arc represents a potential route and therefore a cost. So that matrix of costs you saw on the previous slide are these routes. Okay. Inflow and outflow arrows represent capacities and demands. Okay. So the 10, 15, and 15 on the left represent your capacities. All right, those are the what are available at our sources. Okay, and then the outflow on the right, 8, 10, 12, and 9 represent our demands. Okay, that's what we that is what has to come through those locations. So here's the spreadsheet model. Okay, data at the top as always. Now, In transportation models, we will typically have our decisions in matrix form rather than row form. They can be in a row, but this is a bit more intuitive and a bit easier to understand. Okay, so what I usually do is just copy this part of the spreadsheet up here, down here. All right, and then I take out all of the data and put in my decision cells. On the right is just a calculation, a sum of what's going on here. Okay, row sums, column sums, which represent the totals that are sent and the totals that are received at the locations. Our total cost is a sum product. Okay, it's a sum product of this times this. Okay, with sum product you can do a matrix times a matrix. Okay, as long as they are the same size. All right. Now, in terms of supply and demand in a transportation model, demand usually represents a greater than, it's usually a minimum, okay? And supply is usually a maximum. So, for example, this right here is just a transposition of what we've calculated here. And this at supply is just a reference to these sums here. And then, of course, on the right-hand side, they are these values from the data. Okay, you follow that? And typically, our objective is to create as I said before, is to fulfill demand using the routes that will result in the lowest cost. And of course, we have to stay within our capacity. Okay. The optimum values are not always integers. Okay. But we can constrain them as such if we want to. There is an integer constraint in Solver. We don't really have to worry about integers too much just yet, though. We'll get to integer programming later on. So if you end up with fractional values, don't worry about that unless the problem specifically states that they need to be integers. Now, let's take a look at the formulas. Anytime you're in an Excel spreadsheet, if you do Control tilde, the tilde is the key, the upper value of the key to the left of the 1 on your keyboard. It will show you all of your formulas, okay? And it can be handy. So as you can see, for my demands, to see if we meet demand, these are vertical sums, okay? Over here on the right, we have horizontal sums, okay? This is this value is everything that is sent from each source. These values are everything that is received at each location. Here, the sum product is the sum product of this matrix times this matrix of costs. And then down here, we have simply cell references. Okay, no sense calculating them again. All right, we run Solver and we get our answer. So now let's take a look at something we call the assignment model. And it is essentially a transportation model, but it's a little bit different. It has an equal number of sources and destinations. So it's going to look like a square, okay? And all capacities and all demands equal 1, okay? In other respects, it is the same as the classic transportation model. So here we have Europa Auto, and they have 6 plants and they have 6 products, and they want to decide which products to build at which plants. And the constraint is that there is only one product per plant. Okay, so compacts will only be built at one plant, and one plant will only build compacts. Okay, so the constraints are one all the way around. So here's our flow diagram. All right, equal number of sources and destinations, all of the lines or arcs drawn between them, all capacities and demands equal 1. And here's the algebraic model. Okay, supply, if you'll note, supply is always going to be a less than in a transportation model, and demand is always going to be a greater than. Okay, and so for supply, all of the A's are going to add up to less than or equal to 1. All of the B's are going to be add up to less than or equal to 1, and so on. Whereas down here, it's A1, B1, C1, D1, and so on. All right. Now, again, if the algebra helps you, go for it. If it does not, don't worry about it. I use it sometimes I do not. So here is the spreadsheet model. Okay, now again, with the transportation model, the decision variables usually take the form of a matrix rather than a row. Okay, and so our decisions are binary, if you will, yes or no. And so each one, so for example, take a look down here. Compact is only going to have one in the column. Flint is going to make the compacts. Flint is not going to make anything else. Evansville is going to make the truck. The truck will not be made anywhere else. So you see how it goes. And of course, the total cost is again just the sum product of this matrix times this matrix, and we of course are trying to minimize cost. All right, so the constraints, if you look over here, all right, Akron, Buffalo, Columbus, Detroit, Evansville, the constraint is simply a reference, okay, on the left-hand side. For the row, so it was column to column, and that works fine. For the row, we use the transpose function in Excel if we want to copy and paste an entire row of references. And when we get to our synchronous session, I will show you how to do that. Okay, but again, on the supply, they're all less than 1. Those are the things in red, and on the demand, it's greater than or equal to 1. Okay, and that will of course result in ones everywhere, which is what we want. So the assignment model that we've just seen has a number of different applications. We can assign different swimmers to different positions in a medley relay. We can assign workers to different shifts, courses to time slots, airline crews to flights, and so on. The whole point is that we've got to be able to assign some type of quantitative value to each combination. Otherwise, we won't be able to discriminate between them. Let's take a look at the transshipment model. And this is important for supply chain management, and it is a more complex version of the transportation model. It's actually not that complex, but it is certainly less simple than the Goodwin model that we just looked at. There are 2 or more stages of flow, as there often are in supply chain management. So for example, companies often ship from one manufacturer to a distribution center and then on to the final destination. Okay, so let's take a look at the DeMont Chemical Company. All right, we have a plant shipping to distribution center. Okay, we have distribution centers then shipping to warehouses. All right, and this is our flow diagram. Our plants on the left, each with their own capacity. Plant 1 has a capacity of 2,400, Plant 2, 2,750, Plant 3, 2,500. They will ship to the distribution centers, and then the distribution centers will then send things on to the 5 warehouses. And of course, these numbers on the right represent the demands, at each of the warehouses. Okay, so as I said, this is not terribly complex, but it just adds another stage of network flow. Okay, so this looks a little bit complicated. This is the spreadsheet model with the solution, but it's not. It's a two-stage system, so we have two sets of decision variables. At the top, we have the decisions of how much to send from each plant to each distribution center, and at the bottom, we have the decision of each distribution center how much to send to each warehouse. And of course, we determine that by our capacities, our plant capacities, and our warehouse demands. Okay, so there. Notice that we have flipped the flow of the spreadsheet a little bit. Typically, in a transportation model, you will go from rows to columns. So the sources are almost always in the rows, and the columns are the destinations. We didn't do that down here. We're flowing from the distribution centers to the warehouses. There's no technical reason why we have to do it one way or another. The reason we've done it this way is so that the distribution centers line up in the model. It just looks better. Okay. And so that's typically the way it is done. So there is one other constraint that you might have missed, and that's this one here. Okay, we have totaled up everything coming into a distribution center on top and everything flowing out of a distribution center on the bottom, and they have to be equal. So that is an additional constraint. Everything that goes into a DC has to come out of the DC. All right, in one way or another. All right, and so at the bottom, our total cost is again a sum product, but in this case, it's actually a sum of two sum products. This one times this one, plus this one times this one. Okay, and that's it. We're going to talk about something that's important when we talk about transportation models, and that is the use of balance equations. A balance equation, and we saw it a little bit in the previous slide, is when everything flowing into a node equals everything flowing out of the node. Okay, so the transportation model lends itself to the row and column format, the matrix format. Okay, but not all networks models are best represented this way. Okay, but rather in the single row format that we started with. These models feature the use of balance equations pretty exclusively, especially like with the flow of money, for example. And a balance equation simply means the flow out minus the flow in equals zero. Okay, so that's pretty straightforward. Okay, but it's sometimes difficult to remember that convention. In fact, the author of the text doesn't always follow it perfectly. Okay, but typically it is flow out minus flow in equals zero. So let's take another look at Europa Auto. We've already done this one once using the standard row and column or matrix format. But if we want to use balance equations, then which the assignment model is suited for, then we put our decisions in a single row in standard linear programming format. And as you can see, the row essentially consists of these decisions A1 through 6, B1 through 6, C1 through 6, and so on. And what this represents is A1 means that if we decide to build car number 1 in Akron, A2 means if we decide to build the coupe, which is car number 2, in Akron. Okay, so in each set of 6 decisions that start with A, there will be one 1 because we can only have one of those chosen for Akron. In the for Buffalo, we only have one 1. And for Columbus and so on. All right, our sum product is going to be or our objective is the sum product going to be our decisions times our costs. And those costs were pulled right out of the previous slide. Okay, our constraints. Notice the configuration of the ones. We have to have a 1 everywhere there's, for Akron, we have to have a 1 every place there's an Akron decision. We have to have 1s every place in Buffalo where there's a Buffalo decision. And over on the right, we have our sum products, all right? And we constrain them to exactly equal 1. So in other words, we can never choose more than one car for Akron. We can never choose more than one plant for any one of the cars. Okay? So this is an effective use of balance equations. And the objective turns out to be the same as when we did it in the previous manner. So let's take a look at Goodwin Manufacturing again and see if we can use balance equations on this one. All right. As you recall, we have our sources on the left and our capacities, and our destinations on the right with their demands. Now, can we use balance equations? At first glance, it would look like we cannot, because we have a capacity of 40 total on the left and demands totaling 39 on the right. 40 does not equal 39, so doesn't look like we can use balance equations because balance equations require equality. All right, but we actually can. We have to play around with it a little bit. We can create what's known as a dummy node, okay, that will take up the unused capacity. All right. Now, you might be asking, why would I want to do this? And as a matter of fact, you may not. All right. This is just to show you how it's done. It doesn't mean that it has to be done. It's just that we can modify most transportation problems or network problems to use balance equations. And so we assign no cost to the dummy node because it is virtual flow. Okay, nothing is really moving. All right. So when you have zero cost, you guarantee that you will use that node for the proper amount of capacity. Okay, because it's zero cost. All right. So the system will automatically utilize that route when and where it can because it's the minimum cost. Okay, so let's take a look at it in a little more detail. The constraints for balance equations means flow out minus flow in equals zero. So the capacity for site M is it in Minneapolis, Minnesota? I can't remember, but anyway, the flow for site M is it has a capacity of 10. So that means everything coming out of it, the sum of what goes to A, B, C, D, and N, our dummy node, is 10. Okay, so in terms of algebraically, it looks like this, but the way the linear solver works, we don't like this number hanging out here on the left-hand side, so we add it to both sides, and so we ended up having it on the right-hand side. Okay, we always want numbers on the right-hand side and formulas on the left-hand side. In terms of demand, okay, again, flow out minus flow in equals zero. So Akron, is it Akron? I forget. Has a demand of 8. Okay, so that means everything coming into it, M plus P plus T, has to equal 8. Okay, this is how we write it here. Flow out, which is 8, minus MA minus PA minus TA equals 0. Now we take the 8 and we move it to the other side because that's the way we like to put the model, and so that ends up being our constraint for our demand. Okay, go back and watch this a couple of times. You got to get your head around this. All right, but once it clicks, it'll be pretty easy for you. So here's our spreadsheet model with a solution for Goodwin Manufacturing using balance equations. Again, it's in row format now, like we do with linear programming. Okay, we have our source and destination combinations all the way over here. All right. Notice that we have an MN, a PN, and a TN. The N stands for nowhere. Okay, this is the if you're familiar with Alaska, these are the bridges to nowhere. Okay, and the associated costs. All right, and again, take note that when you go to nowhere, there's no cost involved. Okay, and we actually set this up in standard format in terms of capacity. All right. Everything from Minnesota, anything that starts with an M has ones here, and it has to equal 10,000. Anything from Pittsburgh, okay, has to equal 15,000, and so on and so forth. Notice that they're all equalities. That's the way balance equations work. And at the bottom, we have a capacity of 1, okay, and so nowhere gets filled up. And it looks like it gets filled up from Tucson, okay? Doesn't matter where it comes from, okay? But again, our total cost is going to be our sum product of costs times decisions, and it is the same as when we figured it out in the previous manner. So that's how to do it with balance equations. Again, you might be saying why. All right. At this point, you may not want to do it this way. All right. Not every network model lends itself to balance equations. Okay. Some do and some don't. But they all can be done with balance equations if you have to. Now, we've assumed that network models that are using balance equations, we assume that the amount flowing out of a node equals the amount flowing into the next node, okay, along the arc. But in fact, that's not always the case. We can still use network models even if that assumption is violated. So we have yield loss, okay, shrinkage along the arc, which is possible. There are some processes or transportation models where you have losses along transportation routes, and in some cases you have a yield gain or growth along the arc. And we can accommodate both of those with network models. So let's take a look at Goodwin again with a yield loss. Okay, so we have a loss per route. All right, so for example, from Minneapolis to Atlanta, we expect to lose 24% of whatever it is that we are shipping. Okay, maybe it's dry ice. It doesn't really matter, but we have some way of quantifying the loss per route. So here's our flow diagram. We have, it looks very similar to the ones that we've already used, okay? But we have, on the left-hand side, we have capacities of 16 for each of our sources. And on the right, we have demands of 8, 10, 12, 9, and unknown at the dummy node, okay? Because we don't know what routes we're going to take, so we don't know what our unused capacity is. So it has to remain a variable at this point. We can't assign a number to it. All right, so our unused capacity is unknown. So here are our constraints for the Goodwin model with the yield loss. All right. On the capacity side, we'll just use Minnesota for example. Capacity is 16,000, right? Flow out minus flow in means that you end up with MA plus MB plus MC plus MD plus MN equals 16,000. That makes sense, right? Everything coming out of M has to equal what goes into M. Right now we have no losses yet. We're really basically looking at this point, right around here. Okay? On the demand side, we start having to take into account our losses. All right? So we have a 24% loss from Minnesota to Atlanta. Okay? We have a 10% loss from P to A and a 26% loss from T to A. All right? And so I've skipped a little bit of the algebra, but you can go back and work that out if you need to. Now, for nowhere, it's a little bit different, right? Because we don't know. Nowhere, remember, is a dummy node that will take up our unused capacity. But in fact, since we don't know what routes we're going to take yet, we don't know what our unused capacity is going to be. All right? Because we don't know how much loss we're going to occur. So we have to leave our, on the demand side, we have to leave it as NX as an unknown. All right? And we don't like unknowns on the right-hand side of our equations. Okay, so we have to add nx back to the left-hand side. And so we end up with this, minus mn minus pn minus tn plus nx equals 0. Okay, and that's the form that our model will take. So for now, in this model, our unused capacity is actually a decision variable. All right, because we don't know it. It is not a constant. So this is our solution. Okay, notice that it looks very much like the previous one, except it takes the same form, except we've got our losses built in here. So instead of just ones, for example, we have minus 0.76, minus 0.81, minus 0.93, and so on. It all takes the form of flow out minus flow in equals 0. All right? And so we have our decisions and our total cost. So that's how you do it with a yield loss. All right. You can actually have yield gains, and the most intuitive example of a yield gain is with money. Okay, investment interest, for example. So in this particular example, we're going to use planning for college. College begins in 4 years. All right. So the year one expense for college is going to be 24,000, increasing by 2,000 every year. The questions that we have to decide is how much to invest initially and how much in each investment and when to invest. So we have 4 investments, A, B, C, D. A is available every year. B is available in years 1, 3, 5, and 7. C is available in years 1 and 4. And D is only available in year 1. They mature at different rates. A matures in 1 year, B matures in 2 years, C in 3, and D in 7. And they have different returns also. So A is available every year, and every year it returns 6%, which is pretty good. I wish I had investments like this. So here's our flow diagram. We have 7 nodes, 0 through 7, representing the 8 years, the 4 years before college and the 4 years once college has begun. IO represents our initial investment. All right, we basically put this in at the beginning, at year 0. Okay, our yearly expense is at the end of each of the 4 years. Remember, it starts at 24 and it goes up by 2,000 every year. All right. And so we can see that A is available every year. Investment B is only available every 2 years and matures in 2 years, and so on, according to the data from the previous slide. Okay, so we have our direction. All right, and we're going to gain money along each of these arcs, B1, C1, D1, and so on. Or at least that's the theory. The algebra looks like this. Okay? At the end of year 0, we take a look at flow out, A1, B1, C1, D1, minus flow in, IO, equals 0. Remember, if you always keep in your mind flow out minus flow in equals 0, it helps you build your constraints very easily. All right? So at the end of year 1, which is right here, the only thing we've got coming out is A2. So flow out is A2 minus 0.106 times A1. That's our 6% return. And then it equals 0. And so you can follow the algebra the rest of the way through the end of year 7. Okay? And so this is how it works. Again, it looks a little bit daunting, but it's actually simple algebra and simple drawing. Okay, you just got to practice a little bit to get your head around it. And here's our solution. Okay, we have our data up at the top. We have our decisions, how much to invest initially and how much to invest in each one of the of the investments. Again, A1 through A8, because it's available every year, we only get to invest 3 times in B. We get to invest twice, potentially, in C and once in D. Okay? And our objective is simply the total. Okay? It's our total. Actually, our objective just is our initial investment. We want to minimize our initial investment that will allow us to pay our bills each of the 4 years. Okay, so in this case, our objective is not a formula at all. It's simply a cell reference to our initial investment. And so at the bottom in the constraints, you can see these are all balance equations. All right, everything is inequality. All right, and so go through this and make sure that you understand it. Now we add a little bit of a wrench in the process, and that is models with transformed flows. Okay, in the production process, for example, you transform raw materials into finished goods, for example. So you end up with different inputs and outputs. So in this case, in the flow diagram, the nodes represent a process that transforms certain inputs into certain outputs. And so the units of measure may actually vary as you go in and out of nodes, and that makes sense, right? So let's take a look at Delta Oil. This is a beauty. You're going to love this example. It's pretty complex, all right? But if you break it down, take it step by step, it makes sense. Crude oil is separated into 60% distillate and 40% low-end byproducts. The distillate is separated into gasoline and feedstock for something called the catalytic cracker. The cracker produces gasoline, catalytic gasoline at 64%, and high-end byproducts at 40%. Notice that that's more than 100%. That's okay. All right? This works fine. Gasoline is blended with catalytic gasoline to produce regular and premium gasoline. Okay? Moving on. Here's our flow diagram. All right? We were able to build this flow diagram out of the previous data. Okay? The crude going into the tower, it's separated to distillate and low-end byproducts. All right? Then it is separated into blending for gasoline and feeding the feedstock. At the cracker, it produces high-end product and catalytic gasoline. And from then on, it is blended into premium and regular gasoline. So these are the node constraints. Flow out minus flow in equals 0. Always keep that in the back of your mind. So at node T, which is the tower, the distillate minus the 60% of the crude equals 0. Low end minus 40% of the crude equals 0. And so on. I'm not going to read the whole thing to you, but I want you to kind of, if you have to print these out and look at them, obviously it's in the text. Make sure you understand the process. You're not going to be able to build this from memory, but you don't need to. So we have other constraints. All right. The tower and cracker capacities are 50,000, and 20,000 barrels per day, respectively. There is a sales ceiling for regular and premium of 16,000 each. Never sell more than that. There is an unlimited demand for byproducts. There is a minimum catalytic and regular blend of 50% and a minimum catalytic and premium blend of 75%. These all have to go into the model. Other parameters. The cost of crude is $28 a barrel. The cost of the tower is $5 a barrel for everything it processes. The cost of the cracker is $6 a barrel for the feedstock that it produces. The revenue for low-end and high-end byproducts is 36 and 44, and the revenue for regular and premium gas is 50 and 55 respectively. And here is the model with the solution. Okay? So as you can see, I'm not going to take you through this entire thing here, but the tower separates into 60% distillate, 40% low end. That's why you've got the 0.6, 0.4, and the 1 and 1. all right? And we're using balance equations, okay? At the cracker, it's minus 0.64 and minus zero point 0.4. Again, that is a yield gain, all right? That's okay. That works out. So, and then the other nodes. And then capacity, demand, and blending are regular constraints, just like we've been seeing all along. They are not balance equations. All right, so we can mix balance equations and regular constraints in the same model. All right, and our total profit ends up being 466,400. Okay, and so this is a really complex model. If you take it piece by piece, it makes sense. So break it down and spend some time with it. Okay, and this really shows you the power of optimization, that you can put this many parameters, this many decisions in, and come out with an optimal solution. So that's it for chapter 3. In summary, we've added a fourth basic linear programming model, the network model, to the ones that we've already covered, the allocation, covering, and blending models. And as you've seen, a lot of the models that we end up working with in real life end up being some kind of a hybrid of these four. Okay. In this particular case, the use of flow diagrams are really useful and, in fact, often necessary for solving a network model. And in some cases, balance equations are a key part of creating the flow diagrams and the models. So keep them in mind. And that's it. We'll see you in chapter 4.